We are moving to section 5.4. We're still in systems of equations, but we're going to be looking at solving special systems. We're going to be looking at some of the special cases that can occur when you're solving a system of equations. So let's take a look at that. So when we're solving a system, keep in mind when you're talking about the graph of a system of equations, we're looking for that point of intersection, okay? And most, or if not all of the systems that we've seen so far, there was one solution. We'd have that one ordered pair, that one xy coordinate. That would be our solution. They're intersecting at one point. But we also have the cases, which are our special cases, of no solution and infinitely many solutions. So a system of equations has no solution when the lines are parallel. Now keep in mind, parallel lines mean that we have the same slope, but different y-intercepts. Okay, so you can either take a look at the graphs, or you'll see what happens when we go ahead and we solve the systems when we have that no solution case. But keep in mind, when we're thinking about the graphs, we're talking about lines that are parallel. When we have parallel lines, obviously there's no point of intersection and there's no solution. We also have the case when there's infinitely many solutions. And in those cases, the lines are exactly the same. In essence, they're intersecting at every single point, meaning every single value of x and y is a solution to that particular system. So let's take a look at example number 1. Now I can see right away in example number 1, they're both in y equals. I have the same slopes of 2, and I have different y-intercepts of +1 and -5. So right away, I'm able to recognize that these two lines are going to be parallel, and there's going to be no solution here. Now, I want to just show you what would happen if you didn't recognize that right away, and you went ahead and you solved this using one of the techniques that we've used. So for example, the best way to solve this would be to use substitution, because I have both of my equations solved for y. So I'm going to take this and I'm going to plug it in for y in my second equation. I'm going to get 2x plus 1 is equal to 2x minus 5. Now, if I go ahead and I solve this, I could solve this by getting rid of 2x over here. What ends up happening here is it cancels on both sides. So what you're left with is 1 is equal to -5. Now, obviously, this is not true. This is a false statement. 1 is not equal to -5. So when you're in that situation where your variables cancel out and you're just left with that, that final sentence there, if you end up with something that's not true, that means that there's no solution to your equation. Now, I want to just show you the representation of the graph of this. If we take a look at the graph, I'm going to head to Desmos. We've got y equals 2x plus 1 and y equals 2x minus 5. We can see that these two lines are parallel and they're never going to intersect. So if they're never going to intersect, we have no solution. Let's keep going. Second example here. Okay, I see in this example, the easiest option here, probably to use elimination. You could solve for y in your top equation, but I'm going to use elimination just so we remember how to use that technique. So I want opposite signs, and I'm going to multiply my top equation by -2. So when I do that, I'm going to get 4x minus 2y is equal to -6. Now my bottom equation is -4x plus 2y is equal to 6. Now I could add my two equations together. And if you notice what happens here is both your x's cancel, 4x plus -4x is 0x, and your y's cancel, -2y plus 2y is 0. So you end up getting 0 is equal to, and then on my right-hand side, -6 plus +6 is 0. So your variables all canceled out, and now you're left with a true statement here. So in this particular case, when your variables cancel out, you know you're going to have a special case. In this case, our answer is infinitely many solutions or all real numbers. Meaning any ordered pair is a solution to this equation. And if you take a look, let's head back to Desmos. It's not so obvious right away that these are the same line. But if we go ahead and we graph these, negative 2x plus y is equal to 3. And then we graph our second line, which is negative 4x plus 2y is equal to 6. Notice that the blue line went exactly right on top of the green line, meaning they are exactly the same line. They're intersecting at every single ordered pair, and there's infinitely many solutions to this particular graph. And we prefer that you use infinitely many solutions when describing your solution set. We'll try these in class. Let's look at our last example here. Our last example says the perimeter of a trapezoid poise of land is 48 kilometers. The perimeter of the rectangular piece of land is 144 kilometers. Write and solve a system of linear equations to find the values of x and y. So if we look at our trapezoid piece right here, let's write our equation for our perimeter. Remember, perimeter is just the sum of all the sides. So in this case here, the sum of the sides would be 6y plus 2x plus 6y plus 4x is equal to 48. So this is my trapezoid. And then for my rectangle, I'm going to have 9x plus 18y plus 18y plus 9x is equal to 144. Let's combine our like terms on both of these. So for our trapezoid, combining the y's and the x's, you're going to get 12y plus 6x is equal to 48. And then for the rectangle, you're going to get 36y plus 18x is equal to 144. Easiest option here is probably to solve this by elimination. So in order to do that, I'm going to go with my x's here, and I'm going to get this 6 to become a negative 18. So I'm going to multiply my entire top equation by negative 3. My new top equation now is going to be negative 36y plus 18x is equal to negative 3 times 48 is negative 144. My bottom rectangle equation stays the same at 36y plus 18x is equal to 144. Oops, sorry, this should have been in my top equation because I multiplied by negative a minus 18x. Now, I can add my two equations together. And look what happens here. We cancel with our y's, negative 36 plus 36. We cancel with our x's, negative 18 plus 18, so I'm left with 0, is equal to negative 144 plus 144 is 0 as well. So it cancels with my my constant terms as well. So I end up with a true statement here of 0 is equal to 0. And that means that there's infinitely many solutions to this particular problem. Now, I want to make note though, just because there's infinitely many solutions, there are actual values that are solutions. So in order to figure out one potential solution to this, which is a question that you might see, we want to take a look at the graph. So let's take a look at the graph here. Let's graph 12y plus 6x equals 48. If we take a look at this graph here, all of these values are solutions here. And notice it's the same if we graph our other equation, 36y plus 18x equals 144. You're going to see it's the same exact equation. 36y plus 18x equals 144. Notice it's right on top of it. But there are actual solutions to these. And you have to be careful here because some of these solutions don't really make sense, okay? In terms of the values for x and y, because we're talking about measuring in perimeter. So we can't really have negative values for x or y. So none of these points really make any sense. But a point like, for example, 4, 2 is one potential solution. So having an x value equal to 4 and a y value equal to 2 is one possible solution here. So only the values in here are really solutions that make sense to this actual system of equations. So while there's infinitely many solutions for x, that doesn't necessarily mean in the context of this particular problem that every single value is a solution. So for example, the point -40, 10 would not be a solution. There's just infinitely many of them because lines go on forever and ever and ever. So just to recap here, in this particular lesson, we're looking at some of the special cases. When we think about the graphs in a system, remember we could have one solution if they're intersecting at one point, no solution if we're dealing with parallel lines, and infinitely many solutions if we have lines that are exactly the same. When you're solving these, and you're solving using one of our techniques that is not graphing, you know you're going to be in one of our special cases when both of your variables end up canceling out. When both variables cancel out, you know you have a special case, and depending on whether it's a true statement or not a true statement, you'll either have no solution if you end up with something that's not true, or infinitely many solutions if you end up with something that is true. Good luck, guys. I'll see you in class.